Today we're going to look at the formation of the bright line spectra. Each element is going to produce a unique bright line spectrum because the energy level transitions for each element is unique. On your reference table, you'll see some of the energy levels for hydrogen and for mercury. For hydrogen, it lists the energy levels as N equals different numbers. On the mercury, it gives them as letters. When you're doing problems, just make sure you're looking at the correct element. So the ground state of hydrogen does not have the same amount of energy as the ground state of mercury. The energy levels for every atom are different, and that has to do with the number of protons and the number of electrons in that element. So you'll remember from chemistry that in order to go to an excited state, the electron has to absorb a certain amount of energy. And when it releases that energy, it falls back down to the ground state, or at least to a lower energy level. Sometimes an excited electron can undergo multiple different drops as it goes back down toward the ground state. What we're going to do here is look at determining what frequencies of light we're going to get from a specific element. So knowing what those energy levels are, we can actually predict what the emission spectrum will be for that element. So here is a picture of the hydrogen energy level diagram that's on your reference table. So we've got energy level 1. The ground state is negative 13.6, N equals 2 is negative 3.4, etc. So to figure out what the frequency or what the wavelength is for a photon involved in an electron transitioning from one state to another, there's a couple of steps you're going to do. The first thing you need to do is, looking at this energy level diagram, find the energy in electron volts, because this diagram is in electron volts, that's emitted as the electron falls down from a higher energy level. So you're going to find the difference between the two energy levels that we're transitioning between. Once you have that in electron volts, that's the energy. We do have the equation E equals HF, or E equals HC over lambda, but that energy is in joules. So once you have that energy in electron volts, you need to convert it to joules. And that conversion factor is on the front of your reference table. So if you go down toward the bottom of the list of physical constants, it tells you that 1 electron volt is equal to 1.60 times 10 to the negative 19 joules. So you're going to do a one-step unit analysis to go from electron volts to joules. That gives you the energy in joules, and you're going to simply plug that in to E equals HF, or E equals HC over lambda, depending on whether you're looking for the frequency or the wavelength. So let's do one example together. Let's look for the frequency of the photon that is emitted when an electron falls from N equals 2 to N equals 1 in a hydrogen atom. So the first thing that we'll do is look up the energy for N equals 2 and N equals 1. N equals 2 is negative 3.40. N equals 1 is negative 13.60. So that means the energy is the difference between those two, which would be 10.20 electron volts. So now we have the energy of that photon in electron volts, but we need to convert that to joules. So off the front of your reference table, you can get that conversion factor. 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. So then we're going to plug that into our calculator. 10.2 times 1.6 times 10 to the negative 19 gives us 1.632 times 10 to the negative 18th joules. And I'm not going to worry about significant figures yet because this is not my final answer. But it would only have 3 from the 1.60 in the conversion factor. Then we're going to simply plug into the equation. E equals HF. We're trying to solve for F, so that means F is equal to energy over H. We already have energy in our calculator, so we're going to simply divide that by H, which is also on the front of your reference table. 6.63 times 10 to the negative 34th. And that gives us a frequency of 2.46 times 10 to the 15th hertz. If we wanted to find the wavelength, then we would just plug into the E equals HC over lambda equation.